Imagine a single particle of light, a photon, leaving the surface of a distant star. That star is so far away that its light takes 4 years to reach Earth. 4 years of travelling through the cold vacuum of space. 4 years of crossing the incomprehensible distance between there and here. But here's the strange thing. For that photon, no time passes at all. Not 4 years, not 4 seconds, not even a single instant. For light, the journey from a star 4 light years away takes exactly 0 time. The departure and the arrival are the same moment. The distance doesn't exist. This isn't poetry, this isn't metaphor, this is physics. This is what Einstein's theory of relativity tells us about the nature of light, time, and space. And it's one of the most beautiful, mind-bending ideas in all of science. Think about what this means for a moment. Right now, as you read this, photons are streaming toward Earth from every direction. Photons from the Sun, which left about 8 minutes ago by our clocks. Photons from Proxima Centauri, which left about 4 years ago. Photons from the Andromeda Galaxy, which left 2.5 million years ago. Photons from the edge of the observable universe, which left over 13 billion years ago. By our measurement, these photons have been travelling for vastly different amounts of time. Some for minutes, some for billions of years. But from each photon's perspective, the journey was identical, instantaneous, 0 time. No waiting, no travelling, just existence at the moment of creation, and then, in the same moment, existence at the moment of absorption. All those billions of years of cosmic history compressed into a single instant for the photon experiencing it. That's weird. That's deeply, fundamentally weird. And understanding why it's true will take us on a journey through some of the strangest and most beautiful ideas in physics. So let's explore it. Let's understand why light experiences no time. Why, from the perspective of a photon, the entire universe is compressed into a single point, a single instant. To understand why light experiences no time, we first need to understand what time actually is. This seems like a simple question. Time is time. It's what clocks measure. It's the thing that passes while you're waiting. It's the before and after of every moment. We experience time so constantly, so intimately, that it's hard to imagine it being anything other than a fixed, universal backdrop against which events unfold. But Einstein showed us that time is stranger than we ever imagined. Time is not a constant. Time is not the same for everyone. Time is not a river flowing at a steady rate, carrying us all along together. Time is flexible. Time is personal. Time depends on how fast you're moving. This is called time dilation, and it's one of the most counterintuitive discoveries in the history of science. Let me tell you how Einstein figured this out. In 1905, Einstein was a 26-year-old patent clerk in Bern, Switzerland. He had a physics degree, but couldn't get an academic job. So he examined patent applications by day and did physics in his spare time. That year, he published 4 papers that would revolutionize physics. One of them introduced special relativity. Einstein started with a simple question. What would happen if you could chase a beam of light? He imagined riding alongside a light wave, moving at the same speed. If you could do that, the light wave would appear frozen, a stationary ripple in the electromagnetic field. But this seemed wrong. Maxwell's equations, which describe electromagnetism, don't allow for stationary light waves. Light, according to these equations, always travels at a specific speed. Einstein realized that the resolution to this puzzle was radical. You can never catch up to light. No matter how fast you move, light always travels away from you at the same speed. This meant that the speed of light is constant for all observers. And this simple-sounding statement has mind-bending consequences. If the speed of light is the same for everyone, regardless of how fast they're moving, then something else has to change to make the math work out. That something is time itself. Here's how it works. Imagine two people, one standing still on Earth and one traveling in a spaceship at high speed. Let's say the spaceship is moving at 90% of the speed of light. From the perspective of the person on Earth, time on the spaceship appears to slow down. A clock on the spaceship ticks more slowly than a clock on Earth. If the spaceship travels for what seems like 10 years to the Earth observer, only about 4 years pass for the person on the spaceship. This isn't an illusion. It's not a trick of perception. Time actually passes more slowly for the person moving at high speed. This has been confirmed by experiments. Scientists have flown atomic clocks on airplanes and compared them to identical clocks on the ground. The airborne clocks, moving faster than the ground clocks, showed less elapsed time. Not by much, nanoseconds, but the effect was real and measurable. This isn't just a curiosity, it has practical consequences. GPS satellites orbit Earth at about 14,000 kilometers per hour. They're moving fast enough that time dilation affects them measurably. Clocks on GPS satellites tick slightly slower than clocks on the ground, about 7 microseconds per day slower due to their speed. But there's another effect working in the opposite direction. GPS satellites are further from Earth's gravity than we are on the surface. According to general relativity, Einstein's theory of gravity, time runs faster in weaker gravitational fields. This effect makes satellite clocks run about 45 microseconds per day faster. The net result? GPS satellite clocks run about 38 microseconds per day faster than ground clocks. That might not sound like much, but GPS works by timing how long signals take to reach you from multiple satellites. If the timing is off by 38 microseconds per day, your position would be wrong by about 10 kilometers per day. GPS systems correct for these relativistic effects. Every time you use GPS, you're relying on Einstein's theories of relativity. Time dilation is real. It matters. It's not just abstract physics. It affects technologies you use every day. The faster you move, the slower time passes for you. This is strange enough, but here's where it gets truly mind-bending. What happens as you approach the speed of light? Time slows down more and more. At 99% of the speed of light, time passes about 7 times slower for you than for a stationary observer. At 99.9%, time passes about 22 times slower. At 99.99%, about 70 times slower. The closer you get to the speed of light, the more time slows down. The effect follows a curve that swoops upward toward infinity as you approach light speed. And at the speed of light itself, time stops completely. For anything traveling at the speed of light, time does not pass. Not slowly, not a little bit, not at all. This is why photons, particles of light which travel at the speed of light by definition, experience no time. But let's go deeper. Let's understand why this happens. Einstein's special theory of relativity rests on two postulates. Two simple statements that, when followed to their logical conclusions, reshape our entire understanding of reality. The first postulate: the laws of physics are the same for all observers moving at constant velocities. If you're in a smoothly moving train with the windows covered, you can't do any experiment that will tell you whether you're moving or standing still. Physics works the same either way. The second postulate: the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source. This second postulate is the key, and it's deeply strange. Think about what it means. If you're standing still and I'm moving toward you at half the speed of light, and you shine a flashlight at me, how fast does the light approach me? Common sense says it should be the speed of light plus half the speed of light, 1.5 times the normal speed. After all, if someone throws a ball at you while running toward you, the ball approaches you faster than if they were standing still. But light doesn't work that way. The light from your flashlight approaches me at exactly the speed of light. Not 1.5 times, just 1 times. The same speed you would measure. No matter how fast I'm moving, toward the light, away from the light, sideways, I will always measure the same speed for light. About 299,792 kilometers per second. Always. This seems impossible. How can the same beam of light have the same speed for observers moving at different velocities? The answer is that something else has to give. If speed is distance divided by time, and the speed stays the same while the distance changes, then time must change too. And that's exactly what happens. Time dilates, stretches for moving observers in exactly the right way to ensure that everyone measures the same speed for light. This isn't a conspiracy. It's a fundamental property of space-time, the fabric that underlies everything. Before Einstein, people thought of space and time as separate things. Space was the stage on which events happened. Time was the ticking clock that measured when they happened. Space and time had nothing to do with each other. But Einstein showed that this is wrong. Space and time are not separate. They're woven together into a single entity called space-time. You exist in space-time. Everything exists in space-time. Every event, every particle interaction, every heartbeat, every thought is a point in this 4-dimensional fabric. 3 dimensions of space: left, right, forward, backward, up, down. 1 dimension of time: past to future. 4 dimensions total: space-time. And here's the key insight. When you move through space, you affect how you move through time. Imagine space-time as a kind of budget. You have a fixed amount of motion to spend. The technical term is for velocity, but think of it as a budget. You can spend your entire budget on moving through time. This is what happens when you're standing still in space. You're not moving through space at all, so all your motion goes into time. Time passes at its maximum rate for you. Or you can spend some of your budget on moving through space. If you walk, you're moving through space a little bit. That means you have slightly less budget left for moving through time. Time passes very slightly slower for you than for someone standing still. The effect is tiny at walking speed, unmeasurably small, but it's there. As you move faster through space, you spend more of your budget on spatial motion. That means you have less left for temporal motion. Time slows down more noticeably. At 10% of the speed of light, time passes about 0.5% slower for you. At 50% of the speed of light, time passes about 13% slower. At 90% of the speed of light, time passes about 56% slower. At 99% of the speed of light, time passes about 86% slower. The curve sweeps upward, approaching infinity as you approach light speed. And at the speed of light itself, you've spent your entire budget on moving through space. You have nothing left for moving through time. Time stops. That's why photons experience no time. They've spent everything on space. They have nothing left for time. But there's more. From the photon's perspective, distances don't exist either. This is called length contraction. It's the spatial counterpart to time dilation, and it's just as strange. When you move at high speed, distances in the direction of your motion appear shorter. This isn't an optical illusion. The distances really are shorter for you. Space itself contracts in your direction of motion. Let me give you some numbers. If you were traveling to a star 4 light years away at 50% of the speed of light, the distance wouldn't seem like 4 light years to you. It would be contracted to about 3.5 light years. At 90% of the speed of light, the distance would contract to about 1.7 light years. At 99% of the speed of light, the distance would be about 0.6 light years. At 99.9% of the speed of light, about 0.18 light years. At 99.99% of the speed of light, about 0.06 light years. The faster you go, the shorter the distance becomes. And at the speed of light, the distance contracts to 0. For a photon traveling from that distant star to Earth, the distance is not 4 light years. It's not 4 million kilometers. It's not 4 meters. It's not 4 millimeters. It's 0. From the photon's perspective, the star and Earth are in the same place. There's no gap to cross. The starting point and the ending point are touching. This is why light can travel across billions of light years and experience no time and no distance. The journey, from the photon's point of view, doesn't exist. Light from the edge of the observable universe, light that has been traveling for 13 billion years by our measurement, experiences that entire journey as a single instant across 0 distance. The birth of that photon in a distant galaxy and its arrival in your eye are the same moment at the same place for the photon. It's as if the photon teleported, as if space and time folded up around it, bringing the origin and destination together into a single point. This is what Einstein's relativity tells us. This is what experiments confirm. This is the nature of light. Now let's explore what light actually is. Light is both a wave and a particle. This is called wave-particle duality, and it's one of the central mysteries of quantum mechanics. Sometimes light behaves like a wave. It spreads out, interferes with itself, diffracts around obstacles. It has wavelength and frequency like ripples on a pond. Sometimes light behaves like a particle. It comes in discrete packets, photons, that can be counted individually. When light hits a detector, it arrives as distinct particles, not as a continuous wave. Which is light really? A wave or a particle? The answer is both and neither. Light is something that doesn't fit neatly into our everyday categories. It's a quantum object, and quantum objects are strange. The experiment that reveals this strangeness most clearly is called the double-slit experiment. Set up a barrier with two narrow slits. Shine light at the barrier. On a screen beyond the barrier, observe the pattern that forms. If light were purely particles, like tiny bullets, you'd expect two bright bands on the screen, corresponding to the two slits. Particles would go through one slit or the other, creating two separate patches of light. But that's not what you see. Instead, you see an interference pattern, alternating bright and dark bands across the screen. This pattern only makes sense if light behaves like a wave. Waves from the two slits overlap and interfere with each other. Where the waves are in sync, you get bright bands. Where they're out of sync, you get dark bands. So light is a wave? Not so fast. Turn down the light source so that only one photon is emitted at a time. Each photon passes through the apparatus individually. Even with single photons, fired one at a time, the interference pattern gradually builds up on the screen. Each photon lands at a specific point, particle behavior, but over time, the points form an interference pattern, wave behavior. It's as if each single photon goes through both slits at once, interferes with itself, and then lands at a point determined by that interference. This is quantum superposition. Until the photon is detected, it's in a superposition of going through both slits. It's not in one place or the other, it's in both. But here's where it gets even stranger. Set up detectors at the slits to determine which slit each photon goes through. Now you're observing the photon, measuring its path. When you do this, the interference pattern disappears. The light now behaves like particles, going through one slit or the other, creating two bands instead of an interference pattern. Observation changes behavior. The act of measuring which slit the photon goes through forces it to choose a slit. The superposition collapses. This is deeply strange, and it's been confirmed by countless experiments. Light and all quantum objects exist in a superposition of states until they're measured. Measurement collapses the superposition into a definite state. What does this have to do with the timelessness of light? We don't fully know. Quantum mechanics and relativity are our two best theories of physics, and they don't quite fit together. But both theories tell us that light is fundamentally different from ordinary matter. Light doesn't follow the rules we expect. It transcends our categories. Maybe the timelessness of light and its quantum strangeness are connected at some deep level. Maybe a future theory will reveal that connection. For now, light remains beautifully mysterious. Let me take you on a journey through the electromagnetic spectrum. Light, in its waveform, is a ripple in the electromagnetic field. It's an oscillation of electric and magnetic fields propagating through space at the speed of light. These oscillations have different frequencies, and the electromagnetic spectrum spans an enormous range. At the lowest frequencies, we have radio waves. These have wavelengths from about a millimeter to hundreds of kilometers. Radio waves carry music to your car, television signals to your antenna, and communications to spacecraft billions of kilometers away. As frequency increases, we enter the microwave region. Microwaves have wavelengths from about a millimeter to about 30 centimeters. They heat your food, carry cell phone signals, and form the cosmic microwave background, the oldest light in the universe. Higher still, we find infrared radiation. You can't see infrared, but you can feel it as warmth. The heat you feel from a fire, from the sun, from another person's body, that's infrared radiation. Then we enter the visible spectrum, the narrow band of electromagnetic radiation that our eyes can detect. From about 700 nanometers, red, to about 400 nanometers, violet. Red, orange, yellow, green, blue, indigo, violet, the colors of the rainbow. Why can we see this particular band? Because our sun emits most of its light in this range, and evolution shaped our eyes to detect what was most useful for survival. Beyond violet, we enter ultraviolet territory. UV light causes sunburns and enables certain creatures to see patterns invisible to us. Higher still, X-rays. These penetrate soft tissue, but are absorbed by bone, making them useful for medical imaging. At the highest frequencies, we find gamma rays. These are produced by nuclear reactions, radioactive decay, and the most violent events in the universe: supernovae, black hole mergers, neutron-star collisions. All of this is light. All of this is electromagnetic radiation. All of it travels at the same speed in a vacuum, the speed of light. And all of it, every photon across this vast spectrum, experiences no time. The radio waves carrying music to your car, the microwaves heating your food, the infrared radiation warming your skin, the visible light showing you the world, the ultraviolet light from the sun, the X-rays in the hospital, the gamma rays from distant cosmic explosions, all timeless, all eternal in their own frame of reference. You're surrounded by timeless messengers, radio waves from distant transmitters, cosmic rays from exploding stars, the infrared glow of your own body heat radiating out into the room. Each photon on its own eternal, instantaneous journey. Let me tell you about where light comes from. Most of the light in the universe comes from stars. Stars are nuclear furnaces fusing hydrogen into helium in their cores, releasing enormous amounts of energy. This energy starts as gamma rays, the highest energy form of light. But these gamma rays don't escape the star directly. They bounce around inside, being absorbed and re-emitted countless times as they work their way toward the surface. In the sun's core, the temperature is about 15 million degrees Celsius. The pressure is about 265 billion times Earth's atmospheric pressure. Under these extreme conditions, hydrogen nuclei fuse together to form helium. A gamma-ray photon is born. It carries the energy of nuclear fusion. It begins its journey outward. But it doesn't travel far. Within a fraction of a centimeter, it collides with an atom. The atom absorbs the photon, then emits a new photon, possibly at a different energy, possibly in a different direction. This happens again, and again, and again. The photon bounces like a ball in a pinball machine, absorbed and re-emitted countless times. Its path is a random walk through the solar interior. This journey takes about 170,000 years by our measurement for energy to travel from the core to the surface. During this journey, the photon's energy changes. Gamma rays become X-rays. X-rays become ultraviolet. Ultraviolet becomes visible light. By the time energy reaches the surface, it's been transformed. And yet, for each photon in this chain, no time passes. Each photon exists for an instant that contains its birth and death. Once light reaches the sun's surface, it's free to travel through space. From the sun to Earth takes about 8 minutes by our measurement. For the photon, this leg of the journey is also instantaneous. So when sunlight reaches your skin, those photons were created, from their perspective, in the same moment they touched you. Their 170,000-year random walk through the sun and their 8-minute journey through space were, for them, a single instant. Other light has even more dramatic origins. Some light comes from the Big Bang itself. About 380,000 years after the universe began, it cooled enough for atoms to form. Before that, the universe was a hot plasma that trapped light. After that, light was free to travel. Let me explain this in more detail because it's one of the most remarkable stories in cosmology. In the early universe, the first few 100,000 years, everything was so hot that atoms couldn't exist. Electrons couldn't attach to nuclei. The universe was a soup of free electrons, protons, and photons. The photons couldn't travel far. They kept bouncing off the free electrons, scattering in random directions. The universe was opaque, like trying to see through a dense fog. But as the universe expanded, it cooled. And about 380,000 years after the Big Bang, something dramatic happened. The temperature dropped to about 3,000 degrees Celsius, cool enough for electrons to finally attach to nuclei and form neutral atoms. This is called recombination. Once atoms formed, the photons could travel freely. The fog cleared. The universe became transparent, and a tremendous amount of light was released, the afterglow of the Big Bang itself. That light has been traveling through space ever since, for 13.8 billion years. We call it the cosmic microwave background. It fills all of space, coming from every direction. It's the oldest light in existence, a snapshot of the universe when it was just 380,000 years old. When astronomers point their instruments at the cosmic microwave background, they're seeing the universe as a baby. They're seeing the seeds of all the galaxies and structures that would form over the next 13 billion years. And for that light, those ancient photons, the journey has been instantaneous. The moment of release and the moment of detection are the same. Light from the beginning of time, arriving now, having experienced no time at all. The universe is 13.8 billion years old. Light has been travelling since the beginning, and for that light, no time has passed. The universe and the photon have completely different experiences of duration. For us, embedded in time, the universe is ancient. For light, the universe is a single moment. Both perspectives are valid. Both are real. Time is not absolute. This is one of the most profound realizations in the history of human thought. Time is not what we assumed it was. Time is relative. Time depends on the observer. Let me tell you about light cones. Physicists often represent space and time together on a single diagram. Time goes up the vertical axis, space goes along the horizontal axis. Each point represents an event, something happening at a particular place and time. In such a diagram, an object at rest traces a vertical line. It's moving through time, but not through space. An object moving through space traces a tilted line, moving through both space and time. And light? Light traces a line at exactly 45 degrees. This represents the maximum possible tilt, the fastest possible motion through space. These 45-degree lines form cones on the space-time diagram. They're called light cones. Imagine you're at the center of the diagram, the here and now. From that point, draw two diagonal lines going upward and outward. These represent light traveling away from you into the future. Everything inside those lines is your future light cone. Your future light cone contains all the events you could possibly reach or influence. If you sent a signal at the speed of light right now, it would trace the edge of your future light cone. Anything inside the cone could receive your signal. Anything outside couldn't, not even if you had perfect technology. The light simply wouldn't have time to get there. Similarly, draw two diagonal lines going downward and inward. These represent light that could have reached you from the past. Everything inside this past light cone represents events that could have influenced you. Only events inside your past light cone could have sent signals that reached you by now. Only those events are part of your causal history. Everything outside your light cones, the regions called elsewhere, is causally disconnected from you. Events there can't affect you, and you can't affect them. At least, not yet. Not until light has had time to connect you. This is a profound insight. There are events happening right now, all over the universe, that you can never influence and that can never influence you. They're in your elsewhere. They're beyond the reach of causality. Of course, right now is itself a fuzzy concept in relativity. Different observers disagree about what events are simultaneous. But the light cone structure is the same for everyone. It defines the absolute boundaries of cause and effect. Light cones show us the edges of what can possibly matter. They map the structure of causality itself. And light itself travels along the edges of the light cone. It marks the boundary between the causally connected and the causally disconnected. Think about what this means. You, right now, can only see things inside your past light cone. The light from those events has had time to reach you. The Andromeda Galaxy is about 2.5 million light-years away. When we look at it, we see it as it was 2.5 million years ago, because that's how long the light took to reach us. What Andromeda looks like now is outside our past light cone. It's causally disconnected from our present moment. The most distant galaxies we can see are over 13 billion light-years away. When we look at them, we see the young universe, galaxies forming for the first time, stars igniting, cosmic structures emerging. We can never see the present state of those distant galaxies. By the time any information from their now could reach us, millions or billions more years will have passed. Light connects us to the universe, but it also limits that connection. We're trapped inside our light cone, able to see only what light has had time to bring us. The cosmic speed limit is also a cosmic information limit, a causality limit, a limit on what can ever matter to us. And yet, for the light itself, there is no waiting. The moment a photon leaves a distant galaxy and the moment it enters your telescope are the same moment for the photon. Light creates the separation that it doesn't experience. Light defines the boundary that, for it, doesn't exist. Let me tell you about the twin paradox. This is one of the most famous thought experiments in physics, and it illustrates just how strange time dilation really is. Imagine two twins. One stays on Earth, the other travels to a distant star at high speed, then returns. According to relativity, time passes more slowly for the travelling twin. When they reunite, the traveller will be younger than the twin who stayed home. This has been confirmed by experiments with particles and clocks. It's not just theory, it's measured fact. Let me give you some numbers. If the travelling twin went at 50% of the speed of light to a star 10 light years away and back, about 40 years would pass on Earth. But only about 35 years would pass for the traveller. The traveller returns 5 years younger than their stay-at-home sibling. At 90% of light speed, the trip takes about 22 years on Earth, but only about 10 years for the traveller. The traveller comes back more than a decade younger. At 99% of light speed, about 20 years pass on Earth, but only about 3 years for the traveller. The twin who stayed home is now middle-aged. The traveller is still young. At 99.99% of light speed, about 20 years pass on Earth, but only about 3 months for the traveller. The traveller comes back, and everyone they knew is 20 years older, but they've barely aged. The faster you go, the bigger the effect. Approach light speed closely enough, and you can compress centuries into days. This has profound implications for interstellar travel, if we ever develop the technology. The nearest star system, Alpha Centauri, is about 4.4 light-years away. At conventional rocket speeds, the trip would take tens of thousands of years. Nobody's going to make that journey. But at 99% of light speed, you could reach Alpha Centauri in about 4.4 years from Earth's perspective, and only about 7 months from your perspective. At 99.99% of light speed, you could cross the entire Milky Way galaxy, 100,000 light-years, in about 100,000 years, Earth time, but only about 1,400 years, traveller time. Time dilation makes interstellar travel theoretically possible for the travellers. You could visit distant stars within a human lifetime, your lifetime. But here's the catch that makes the twin paradox bittersweet. While you're travelling, time passes normally for everyone back home. If you travel to a star 50 light-years away at 99.9% of light speed, you might age only a few years. But when you return, everyone you knew will be 100 years older. They'll be dead. Your whole world will have changed. Time dilation saves your time, but not theirs. This is the cruel arithmetic of relativistic travel. You can explore the cosmos, but you can never truly go home. Home will have moved on without you. Science fiction stories have explored this poignantly. The traveller returns to find their children are older than they are. The world they left no longer exists. It's the price of touching the timelessness of light. You save yourself from time, but you lose everyone else to it. And if you could travel at exactly the speed of light, you wouldn't age at all. Any journey would take 0 time from your perspective. But there's a fundamental barrier. You can't travel at the speed of light if you have mass. Let me explain why. You can't travel at the speed of light if you have mass. As an object with mass moves faster, it takes more energy to accelerate it further. The closer you get to light speed, the more energy each additional increment requires. At 90% of light speed, you need about 2.3 times as much energy as at rest. At 99%, about 7 times as much. At 99.9%, about 22 times. At 99.99%, about 70 times. The energy required approaches infinity as speed approaches light speed. To actually reach light speed with any massive object would require infinite energy. This is why the speed of light is an absolute barrier for anything with mass. Photons don't have this problem. They have no mass. They don't need to accelerate to light speed. They're born traveling at light speed. They can't travel at any other speed. Photons exist only at the speed of light. Created at that speed, absorbed at that speed. No in between. So we're stuck below the cosmic speed limit. We can get close, we can experience time dilation, but we can never reach light speed. Light exists in a realm we can never enter. Let me tell you about redshift. When a source of light is moving away from you, the light it emits appears stretched, shifted toward longer wavelengths, toward the red end of the spectrum. This is similar to the Doppler effect with sound. When an ambulance drives past, its siren sounds higher pitched as it approaches and lower pitched as it recedes. With light, approaching sources are blue shifted, receding sources are red shifted. In the 1920s, astronomer Edwin Hubble discovered something extraordinary. He was studying distant galaxies, measuring their redshifts, and he found that almost all of them were redshifted. They were moving away from us. More than that, the further away a galaxy was, the faster it was receding. This relationship, velocity proportional to distance, is called Hubble's law. And it has a remarkable implication. If galaxies are moving apart, and if you run the clock backward, they must have been closer together in the past. Run the clock back far enough, and everything in the universe was in the same place. This was the first observational evidence for the Big Bang. The universe had a beginning. It started from an incredibly hot, dense state and has been expanding ever since. Hubble's discovery changed everything. Before him, most people, including Einstein, assumed the universe was eternal and static. After him, we knew it had a history. It was born and it's evolving. And light revealed all of this. Light from distant galaxies, stretched by cosmic expansion, told us the story of the universe's birth and growth. This is what light does. It carries information across the cosmos. It tells us what happened, where and when. And it does this while experiencing nothing itself. No time, no travel, just existence. The cosmic expansion continues today. Space itself is stretching, carrying galaxies apart like dots on a balloon being inflated. And light, travelling through this expanding space, gets stretched along with it. A photon emitted as blue light billions of years ago can arrive as red light or even invisible infrared because space stretched while the photon was in transit. The cosmic microwave background shows this dramatically. When the universe was 380,000 years old, it released hot visible light, about 3,000 degrees, a dull orange-red glow. But space has expanded by a factor of about 1,100 since then. That light has been stretched from visible wavelengths to microwave wavelengths. Today, the cosmic microwave background has a temperature of about 2.7 Kelvin, just 2.7 degrees above absolute zero. The ancient glow of the Big Bang, redshifted across 13.8 billion years of cosmic expansion, now bathes the universe in a faint microwave hum. And for that light, none of this happened. The stretching occurred in our time, not in the photon's timeless instant. The universe expanded around the photon, but the photon didn't experience the expansion. Light carries the imprint of cosmic history without experiencing it. It's like a letter that arrives with a postmark showing it was mailed decades ago, but for the letter itself, no time passed in transit. Let me tell you about the future of light. The universe is expanding, and that expansion is accelerating. This was discovered in 1998, and it was one of the most surprising findings in the history of cosmology. Two teams of astronomers were studying distant supernovae, exploding stars that can be used as standard candles to measure cosmic distances. They expected to find that the expansion of the universe was slowing down. After all, gravity pulls matter together. Every galaxy in the universe is gravitationally attracted to every other galaxy. This attraction should act like a brake on the expansion, gradually slowing it down. But that's not what they found. The distant supernovae were dimmer than expected. They were further away than they should be if the expansion was slowing. The universe was not only expanding, it was expanding faster and faster. Something was pushing the universe apart, overcoming the gravitational attraction of all the matter in the cosmos. We call this something dark energy. It's one of the biggest mysteries in physics. Dark energy makes up about 68% of the total energy content of the universe. It's everywhere, and it's causing space itself to expand at an accelerating rate. We don't know what dark energy is. We don't know why it exists. We don't know why it has the strength it has. But we can see its effects. And those effects have profound implications for the future of light. As the expansion accelerates, distant galaxies are receding from us faster and faster. Their light is being stretched to longer and longer wavelengths. Eventually, billions of years from now, distant galaxies will be receding from us faster than the speed of light. Wait, faster than light? Didn't I say nothing can go faster than light? Yes, but there's an important subtlety here. Objects can't move through space faster than light. The speed of light is the ultimate speed limit for anything traveling through space. But space itself can expand at any rate. There's no limit on how fast space can grow. So distant galaxies can be carried away from us by the expansion of space faster than light can travel through that space. When this happens, the light from those galaxies can never reach us. They emit light, but that light is being carried away by expanding space even as it tries to travel toward us. It's like trying to swim against a current that's faster than you can swim. You'll never make progress. These galaxies pass beyond our cosmic horizon. They become forever invisible to us. Not because they're destroyed, but because their light can never catch up with the expanding space between us. This is happening right now, actually. Galaxies beyond a certain distance are already receding faster than light. We can still see them. We're seeing light they emitted in the past, before they crossed the horizon. But we'll never see what they look like now. And as time goes on, this horizon will creep closer. More and more galaxies will cross the threshold. Their light will be redshifted to oblivion, stretched by expansion until it fades to nothing. Over vast timescales, tens of billions of years, the observable universe will shrink. Our local group of galaxies, the Milky Way, Andromeda, and about 80 smaller galaxies gravitationally bound together, will merge into a single giant elliptical galaxy. Call it Milkomeda or Milkdromeda. And beyond that merged galaxy, nothing. Every other galaxy in the universe will have passed beyond the horizon. Their light will never reach us again. Astronomers living in that distant future will look out at the cosmos and see only their own galaxy. They'll have no way of knowing that the universe once contained 2 trillion galaxies. No way of detecting the cosmic microwave background. No way of measuring cosmic expansion. To them, the universe will appear to be a single island of stars in an infinite void. All the evidence of the Big Bang, of cosmic evolution, of the grand structure of the cosmos, gone. Carried away by dark energy and expansion. It's a haunting vision, a universe slowly going dark, not through catastrophe, but through isolation. But it's also a reminder of how special our cosmic moment is. We live in an era when we can still see the universe's history, still detect the microwave background, still observe billions of galaxies, still measure cosmic expansion. This won't always be true. Future civilizations, born in that isolated galaxy, will have no access to the cosmic story we can read so easily today. So appreciate it. The light reaching us from distant galaxies, from the edge of the observable universe, from the Big Bang itself, it's a gift that won't last forever. Light is the fastest messenger, but in an accelerating universe, even the fastest messenger can be outrun. There's something melancholy about that, but also something beautiful about being alive during this window when the universe's story is still visible. Let me tell you about how we see. This is where the cosmic meets the personal, where timeless photons from across the universe become your conscious experience of seeing. When photons enter your eye, they pass through the cornea, the clear front surface, and the pupil, which adjusts its size to control how much light enters. Then through the lens, which changes shape to focus light on different distances. All of this happens automatically, without you thinking about it. Your eye is constantly adjusting, focusing, adapting. The focused light lands on the retina, a thin layer of tissue at the back of your eye. The retina is essentially a piece of your brain that migrated to your eye during embryonic development. It's neural tissue filled with light-sensitive cells. These cells are called photoreceptors. There are two types, rods and cones. Rods are sensitive to very low light levels. They're what you use when you walk outside on a moonlit night. They don't perceive colour, that's why things look grey in dim light. But they're incredibly sensitive. A dark adapted rod cell can respond to a single photon. Think about that. A single particle of light travelling from a distant star can trigger a response in a cell in your eye. You have about 120 million rods in each eye, mostly around the edges of your retina. Cones work in brighter light and give you colour vision. They come in three types, each sensitive to a different range of wavelengths, roughly red, green, and blue. All the colours you see, the sunset oranges, the ocean blues, the forest greens, are combinations of signals from these three cone types. Your brain interprets different patterns of cone activation as different colours. You have about 6 million cones in each eye, concentrated in the centre of your retina in an area called the fovea. That's why you see colour and detail best when you look directly at something. When a photon is absorbed by a rod or cone, something remarkable happens. A molecule called retinal, which is embedded in a protein called rhodopsin or photopsin, changes its shape. This shape change triggers a cascade of biochemical reactions. The signal passes through several layers of neurons in the retina: bipolar cells, amacrine cells, horizontal cells, ganglion cells, each processing the information in various ways. The retina doesn't just detect light, it starts analyzing the image before the signal even leaves your eye. Finally, the processed signals travel down the optic nerve, about 1.2 million nerve fibers bundled together, to your brain. In your brain, the signals first reach the lateral geniculate nucleus, a relay station in the thalamus. Then they proceed to the primary visual cortex at the back of your head. From there, the information splits into two main streams. The what stream goes toward the temporal lobe, processing object recognition. The where stream goes toward the parietal lobe, processing spatial location and motion. Different areas of visual cortex specialize in different aspects of vision: edges, color, motion, faces, places, words. The image you see is reconstructed from all these specialized analyses. All of this, from photon entering eye to conscious visual experience, takes about 100 to 200 milliseconds. That means you don't see the present, you see the past, a tenth to a fifth of a second ago. Your brain needs that time to process the information. But here's the beautiful thing. Those photons, the ones absorbed by your retina, experience no time on their journey to you. Whether they came from a lamp across the room or a star a million light years away, for the photon, the journey was instantaneous. And then, in your eye, time begins. The photon is absorbed. Its energy triggers a molecular change. Time-bound processes take over. Chemistry, neurons, electrical signals, thought. Your eye is the boundary between timelessness and time, the place where photons end their eternal instant and become something you experience. You are where light meets consciousness. You are where the universe becomes aware of itself. Every time you see something, anything, you're witnessing this transition. Timeless messengers converting into temporal experience. It's happening right now. It happens every moment of every day. Your visual experience of the world is built from timeless information. The colors, shapes, faces, places you see, all carried by particles that exist outside of time. And somehow, in the electrochemical dance of your neurons, it becomes something felt, something known, something experienced in time. How does that happen? How does the objective, timeless physics of photons become the subjective, temporal experience of seeing? That's one of the deepest questions in philosophy and neuroscience, the hard problem of consciousness. We don't have a complete answer. Maybe we never will. But we can appreciate the mystery. Every time you open your eyes, you're doing something miraculous. You're converting timeless light into temporal experience. Let me talk about the speed of light itself. The speed of light in a vacuum, about 299,792 kilometers per second, often rounded to 300,000 kilometers per second, is not just the speed that light happens to travel. It's a fundamental constant of the universe, one of the most important numbers in physics. It appears everywhere. In Einstein's famous equation, E equals mc squared, the c is the speed of light. This equation tells us that mass and energy are equivalent, related by the speed of light squared. A tiny amount of mass contains an enormous amount of energy. That's why nuclear reactions release so much power. In Maxwell's equations, which describe electromagnetism, these equations predict electromagnetic waves that travel at a specific speed. And when you calculate that speed from the constants of electricity and magnetism, you get the speed of light. This was one of the first hints that light is an electromagnetic wave. In the geometry of space-time, the speed of light defines how space and time relate to each other. It's the conversion factor between distance and duration. In quantum mechanics, the fine structure constant, which governs how light interacts with matter, involves the speed of light. The speed of light is woven into the fabric of physics. It's not just how fast light travels, it's a fundamental property of the universe. Why is it 299,792 kilometers per second and not some other value? This is actually a subtle question. In some ways, the specific number doesn't matter. The number depends on what units you use. If you use miles instead of kilometers, you get a different number. If you measure time in something other than seconds, you get a different number. What matters is how the speed of light relates to other things, how it compares to the speeds we can achieve, how it sets the scale for energy and mass. In physics, we sometimes use natural units where the speed of light equals 1. Time and distance are then measured in the same units. This simplifies many equations and reveals the deep connection between space and time. But in our everyday units, meters and seconds, the speed of light has this particular value. And that value has consequences. It means light can circle Earth about 7.5 times in 1 second. It means light from the sun takes about 8 minutes to reach us. It means light from the nearest star takes about 4 years. It means our radio signals, traveling at light speed, have reached stars about 100 light years away, a tiny bubble in a galaxy 100,000 light years across. The speed of light sets the scale for everything: how fast we can communicate, how far we can see, how much of the universe we can ever hope to explore. If the speed of light were different, the universe would be different. Chemistry would be different. Stars would be different. We might not exist. Some physicists wonder if the speed of light could be different in other universes, if such things exist, or if it could have been different in the very early moments of our universe. For now, we don't know why the speed of light has the value it does. It's one of the fundamental constants of nature, a number that defines our reality without explaining itself. But we can appreciate it. This particular speed, this particular number, makes our universe what it is. It enables stars to form, chemistry to happen, life to emerge. And it creates the strange reality that light experiences no time. If the speed of light were infinite, there would be no time dilation. Everyone would agree on time. The universe would be simpler, but stranger in other ways. If the speed of light was 0, light couldn't travel at all. The universe would be dark and disconnected. But at this particular speed, fast but not infinite, we get time dilation, length contraction, and the beautiful physics of relativity. We get a universe where light connects everything but experiences nothing. It's a strange, wonderful balance. Let me tell you about Fermat's principle. Light always takes the path that minimizes time. This is one of the oldest principles in optics, discovered by Pierre de Fermat in the 17th century. And it has a beautiful, almost philosophical quality to it. If light travels through a uniform medium, the fastest path is a straight line. That's why light travels in straight lines through air or vacuum. But if light passes from one medium to another, say from air to water, something interesting happens. Light bends. You've seen this. Put a straw in a glass of water and it appears bent at the surface. Put a coin at the bottom of a pool and it seems closer to the surface than it really is. This is called refraction. And it happens because light travels at different speeds in different materials. Light moves slower in water than in air, about 25% slower. In glass, light slows down by about 30 to 50%, depending on the type of glass. In diamond, light slows by about 60%. When light moves from a fast medium to a slow medium, like air to water, it bends toward the normal, the perpendicular to the surface. When it moves from slow to fast, water to air, it bends away from the normal. Why does it bend? Because bending is faster. If you're running along a beach and need to reach someone drowning in the water, you shouldn't run straight toward them. You should run a bit further along the beach first, where you're fast, then turn into the water, where you're slow. The angled path is faster than the straight path. Light does the same thing automatically. When light crosses from air to water, it realizes that it can get to its destination faster by changing direction. It bends in exactly the way that minimizes total travel time. There's something almost purposeful about this, isn't there? Light seems to know which path is fastest. It seems to choose the optimal route. Of course, light doesn't actually know or choose anything. It's not conscious. The behavior emerges from the wave nature of light and how waves propagate. But the mathematical description that light minimizes travel time is precise and predictive. It tells you exactly how much light will bend at any interface. And here's the beautiful paradox. Light minimizes time, yet light itself doesn't experience time. Light plays a game whose rules it doesn't experience. It optimizes for something that, from its perspective, doesn't exist. From our perspective, light bends to save time. From the photon's perspective, there is no time to save. The journey is instantaneous regardless of the path. It's as if a race car driver optimized their route around a track without being aware that they were racing, or that time was passing, or that there was such a thing as faster or slower. This is one of the strange loop aspects of physics. The description from outside, light minimizes time, and the experience from inside, no time exists, seem incompatible. Yet both are valid ways of understanding what happens. The universe is full of such paradoxes, such beautiful contradictions that turn out to be complementary perspectives rather than genuine conflicts. Light bends to save time it doesn't experience. And somehow, the universe makes sense. Let me tell you about the nature of darkness. We often think of darkness as the opposite of light. Where there's no light, there's darkness. But from a physics perspective, darkness is just the absence of photons. It's not a thing in itself, it's a lack of a thing. When you're in a dark room, your eyes receive very few photons. Your brain interprets this as darkness. But the room isn't fundamentally different from a lit room. The same space exists. The same objects are there. Just no photons bouncing around for your eyes to detect. Darkness is an experience we have when light isn't present. It's our perception of an absence. And yet darkness has its own quality. It feels like something. It's not just a blank. How does the absence of stimulation become a positive experience? How does no photons become darkness rather than just nothing? This is one of those questions that sits at the boundary of physics and philosophy. Physics can tell you that darkness is the absence of photons. It can't tell you why the absence of photons feels like something. That's a question about consciousness, about how physical processes give rise to subjective experience, about the relationship between the objective world, photons or lack thereof, and the subjective world, the experience of light or darkness. It's called the hard problem of consciousness, and it's one of the deepest unsolved problems in science and philosophy. But let me tell you something interesting about darkness from a physics perspective. Even in the darkest place you can imagine, there's still light. If you were floating in the deepest intergalactic void, far from any galaxy, the cosmic microwave background would still be there. Those ancient photons from the Big Bang fill all of space. Even in the darkest void, about 400 microwave photons pass through every cubic centimeter every second. You couldn't see them, they're not in the visible spectrum, but they're there. And there's more. Empty space itself isn't truly empty. According to quantum mechanics, vacuum is seething with virtual particles that pop in and out of existence, including virtual photons. These quantum fluctuations are real and have measurable effects. The Casimir effect, for instance, is a tiny force between two metal plates caused by vacuum fluctuations. It's been measured in laboratories. So even darkness isn't truly dark if you look closely enough. There's always something there. But for practical purposes, for our eyes, for our experience, darkness is the absence of photons in the visible range. When those photons are missing, we experience darkness. And in that experience, something strange happens. We've been talking about how light connects us to the universe, how photons carry information from distant stars, from the Big Bang, from everything we can see. Darkness disconnects us. In the dark, we're cut off from that cosmic information flow. No photons are bringing us images of the world. We're isolated in a way. And yet, we're still connected. Infrared photons from our own bodies radiate outward. Radio waves from distant sources pass through the room. The cosmic microwave background is still there. We're never truly disconnected from the universe's web of light. We just can't always see it. That's worth remembering. Even when you feel alone in the dark, you're surrounded by timeless messengers. They're just invisible to your eyes. The universe is always in touch with you, through light you can't see, through photons that experience no time. Darkness is real, but it's not as absolute as it seems. Let me step back and consider what all this means. Light is the fastest thing in the universe. Nothing can outrun it. Nothing can send information faster. Light is timeless. From its own perspective, it exists in a single instant that contains its entire existence. Light is spaceless. From its own perspective, distances contract to zero. Light is the primary messenger of the cosmos. Almost everything we know about the universe comes from light. And light is strange. It's both wave and particle. It interferes with itself. It collapses when observed. Light is at the center of our two greatest theories, relativity and quantum mechanics, and it behaves strangely in both. Maybe that's not a coincidence. Maybe light's unique nature points to something deep about the structure of reality. Or maybe light is just one weird thing among many in a universe full of weirdness. Either way, it's worth appreciating. Let me tell you about what light does here on Earth. Almost all life on our planet depends on light, not just for seeing, for energy. Plants, algae, and certain bacteria perform photosynthesis. They capture photons from the sun and use that energy to convert carbon dioxide and water into sugars and oxygen. This is one of the most important chemical reactions in the history of Earth. It produces the oxygen we breathe. It creates the food at the base of almost every food chain. It removes carbon dioxide from the atmosphere. And it starts with a photon being absorbed. In a leaf, there are structures called chloroplasts. Inside chloroplasts are molecules of chlorophyll, the pigment that makes plants green. When a photon of the right wavelength, blue or red light mostly, hits a chlorophyll molecule, it kicks an electron into a higher energy state. That excited electron is passed along a chain of molecules, driving chemical reactions that store energy in the bonds of sugar molecules. The whole process is remarkably efficient. Plants capture about 1 to 2% of the solar energy that reaches them. Some algae do even better. This has been going on for about 3.5 billion years. Photosynthesis transformed Earth from a planet with almost no oxygen to one where oxygen makes up 21% of the atmosphere. Without photosynthesis, complex life as we know it couldn't exist. We eat plants, or we eat animals that eat plants. Either way, we're solar powered at one remove, and it all depends on photons. Photons that left the sun 8 minutes ago by our clocks. Photons that were created in nuclear fusion in the sun's core. Photons that, from their own perspective, travelled no distance and took no time. Those timeless travellers power your body. The sandwich you ate for lunch, the breath you just took, all made possible by photons connecting you to a star 150 million kilometers away. Light also shapes our planet in other ways. The warmth we feel comes from infrared radiation, photons at wavelengths just beyond what our eyes can see. The sun's heat is carried by light. Weather and climate are driven by differential heating, the sun warming the equator more than the poles, land more than water. This creates the circulation patterns that distribute heat and moisture around the globe. The ozone layer protects us from ultraviolet light. UV photons have enough energy to damage DNA, causing mutations and cancer. The ozone absorbs most UV before it reaches the surface. The blue color of the sky comes from light scattering. Blue light scatters more than red, so when you look at the sky, away from the sun, you see scattered blue light. Rainbows form when light refracts through water droplets, separating into its component colors. Each color bends at a slightly different angle. The green of plants, the blue of the ocean, the orange of sunset, all phenomena of light interacting with matter, all made of photons doing what photons do. And all those photons, timeless in themselves, create the vivid, colorful, changing world we experience. Every time you see something, you're receiving timeless messengers. Every photon that enters your eye has traveled without experiencing time or distance. The colors you see, the shapes you perceive, the faces of the people you know, all carried by particles that exist outside of time. Your experience of the world, which unfolds in time, which is full of duration and change, is assembled from components that have no experience of time at all. The building blocks of your vision are eternal. The messengers that bring you the world are timeless. And yet here you are, experiencing time, experiencing change, experiencing the flow from one moment to the next. How does time emerge from timelessness? How does our experience of duration arise from messengers that know no duration? These are deep questions. Maybe someday we'll have answers. For now, they're mysteries worth sitting with. The universe is 13.8 billion years old. It contains trillions of galaxies, each with hundreds of billions of stars. And connecting it all is light. Timeless messengers carrying energy and information across the void. Some of that light has been traveling since the beginning. Some was born a nanosecond ago. From each photon's perspective, the journey was the same, instantaneous. Light doesn't care about distance. Light doesn't care about time. Light just is. And through light, we know the universe. Every star we see, every galaxy we photograph, every cosmic structure we map, all revealed by light. The planets by reflected sunlight, the stars by their own glow, the microwave background by ancient heat. Light is how the universe tells us about itself. Without light, we'd be blind to everything beyond our reach. We'd know only what we could touch. Light extends our awareness to the edge of the observable cosmos. It lets us see billions of years into the past. It brings us the story of everything. And it does all this while experiencing nothing. No time, no journey, no narrative. Light is a bridge between our time-bound existence and the timeless depths of the cosmos. When you look at the night sky, you're using timeless messengers to learn about a universe full of time. When you watch a sunset, you're seeing photons that left the sun 8 minutes ago, but experienced no journey at all. When you look into a candle flame, you're seeing photons born in chemical reactions, each beginning and ending its existence in the same instant. Light is everywhere. Light is constant, and light is beyond time. That's one of the strangest, most beautiful things about the universe. The fastest travelers experience the slowest time. The most connected things, photons linking the cosmos, are the most isolated from duration. At the speed of light, the universe becomes a single point, a single moment, everything touching everything else. We can't go there. We're made of mass. We're trapped in time. But we can imagine it. We can reach toward it with our understanding. And in that reaching, we touch something profound. The universe contains perspectives utterly unlike our own, ways of existing we can barely conceive. Light is one of them. And light is everywhere. Every photon in this room, every ray of sunlight, every star in the sky, all of them timeless, all of them experiencing the universe in a way we never will. It's humbling, it's beautiful, it's strange, and it's real. This is the universe we live in. A universe where time is flexible, where space contracts, where light travels without experiencing travel. A universe far stranger than common sense suggests, but also far more wonderful. That's the gift of physics. It shows us the universe as it actually is, not as our intuitions expect it to be. And what it shows us is extraordinary. Light without time, distance without space, a cosmos connected by messengers that exist in a single, eternal instant. This is reality, and you're part of it. Every photon that enters your eyes has made the same impossible journey. Every color you see is carried by something timeless. You are the endpoint of countless instant voyages. The place where light finally stops, is absorbed, and becomes experience. You are where the eternal becomes temporal. You are where light meets time. That's something to think about. That's something to appreciate. The universe is vast and strange and beautiful, and light is how we know it. Timeless light, eternal messengers. The cosmos, communicating with itself through particles that don't experience the communication. It's one of the greatest stories physics has to tell, and now you know it too. Light has no time. Light has no distance. And yet light shows us everything. That's the paradox. That's the beauty. That's the universe. Let me leave you with a few thoughts. We've covered a lot of ground: time dilation, length contraction, space-time, wave-particle duality, the electromagnetic spectrum, cosmic expansion, photosynthesis, vision. But it all comes back to one central fact. Light doesn't experience time. This is not a minor detail. It's not a curiosity for physics textbooks. It's a profound statement about the nature of reality. We live in a universe where different observers have different experiences of time, where speed affects duration, where the fastest thing in existence experiences no duration at all. This is deeply strange. It violates our intuitions at every turn. But it's also deeply beautiful. It shows us that the universe is richer, stranger, more wonderful than we could have guessed from everyday experience. Common sense is just the prejudice we accumulate before age 18, Einstein allegedly said. The universe doesn't care about common sense. It operates according to its own rules, rules that we can discover, test, and use, but that we didn't invent and can't change. Light experiences no time. This is one of those rules. And understanding it connects us to something larger, to the structure of reality itself, to the deep patterns that underlie everything. When you watch a sunset, you're not just seeing pretty colors. You're seeing photons that traveled 150 million kilometers in 8 minutes by our clocks, but 0 time by theirs. You're seeing the timeless made visible. When you look at the stars, you're seeing ancient light that has crossed the cosmos without aging. You're receiving messages from the past, carried by messengers who experienced no time. When you simply open your eyes, you're converting timelessness into experience. You're the end point of countless instant journeys. You're where light becomes awareness. That's something worth appreciating. The universe didn't have to be this way. There's no obvious reason why the speed of light should be finite but unreachable, or why time should dilate with velocity, or why photons should be timeless. But it is this way, and we can understand it. And that understanding is itself a kind of wonder. Physics gives us many gifts, practical gifts, technology, medicine, engineering, but also conceptual gifts, new ways of seeing, new frameworks for thought, new perspectives on existence. The timelessness of light is one of those gifts. It expands our sense of what's possible. It shows us that our intuitive notions of time and space are provincial, limited to the slow-moving, planet-bound lives we happen to lead. At the speed of light, things are different, radically different, and that difference is part of the universe we live in. So next time you see light, any light from any source, take a moment to consider what you're actually seeing. You're seeing timeless messengers. You're seeing particles that have traveled without experiencing travel. You're seeing the universe's way of connecting distant places while remaining outside of time. You're seeing something ancient and strange and beautiful. You're seeing light, and light has no time. And that's one of the most remarkable facts about reality. Carry it with you. Let it inform how you see the world. Let it remind you that the universe is deeper than it appears. Light connects us all. Every photon a timeless thread in the fabric of existence. And now you know why. That's the story of light and time, a story that's been true since the universe began, a story that will remain true until the last star goes dark, a story written in the physics of reality itself, the timeless journey of light. No time, no distance, just existence, just connection, just light. There's something meditative about this, isn't there? In a universe full of complexity, galaxies colliding, stars exploding, civilizations rising and falling. Light is simple. Light just is. It doesn't struggle. It doesn't wait. It doesn't age. Light is the simplest thing in the universe. A quantum of electromagnetic energy. A ripple in a field. No internal structure. No parts to wear out. No time to pass. And yet light does everything. It carries energy. It transmits information. It enables chemistry. It makes life possible. It connects the cosmos. The simplest thing accomplishes the most. There's a lesson there, maybe. Or maybe it's just the way the universe happens to work. Either way, it's beautiful. You live in a universe where time is not what you think it is, where speed affects duration, where the very concept of now is relative to your motion. You live in a universe where light, the thing that shows you everything, experiences nothing. No time, no distance, no journey. You live in a universe where the messenger is timeless, even though the message is about change. These facts have been true since the Big Bang. They'll be true until the last star dies. They're woven into the structure of reality. And now you understand them. That's something. That's a connection to the deep nature of things. That's what physics gives us. A way of seeing that goes beyond the surface, beyond intuition, beyond the everyday. The universe is strange, but it's comprehensible. And in comprehending it, even a little, we touch something larger than ourselves. Light has no time. Distance has no meaning for a photon. And somehow, out of this timeless dance, the universe we experience emerges. Stars form and burn and die. Galaxies spin. Life evolves. Minds arise and wonder about the nature of light. All of it carried by photons that never age. All of it connected by messengers that never travel. That's the universe. That's your home. That's where you are. Right now, reading these words, converted from light into thought. The timeless made temporal. The eternal made momentary. Light becoming knowledge. That's the story. That's always been the story. And now you're part of it. Every photon that ever entered your eyes made you a witness. Every beam of sunlight that ever warmed your skin connected you to a star. Every image you've ever seen was carried by timeless messengers. You are woven into the universe's web of light. You always have been. And now you know what that light really is. Timeless, spaceless, the eternal in motion, the infinite made small. Light. That's the universe's gift to us. And now you understand it. Carry that understanding forward. See light differently from now on. Remember what it really is. Remember what you really are. The place where timeless light becomes temporal thought. The universe aware of itself. Through light. Always through light. This is reality. This is truth. This is the universe, understood. Light without time. Distance without space. You watching. The cosmos connected. One story, forever.